Hello and welcome to the video lecture series on contact mechanics in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. And this is the third part of the second video lecture on contact mechanics, modeling and simulations. And this is also the last part. And here we'll briefly discuss the numerical accuracy and how to discretize the problem in 2D. This is only a short note on the numerical accuracy and the discretization of the 2D contact mechanics problem. And you will also be given an exercise devoted to numerical accuracy of the 1D problem to carry out yourself. It is time to sum up, so we will have a look at the full discretized 1D contact mechanics model, and then a little bit about accuracy and how to discretize in 2D. So what we have until now is a discrete representation of our complementarity problem, and it's looking like this. And then we have the discrete representation of the force balance equation just below here. And we know also that we can compute the auxiliary part of this deformation as K times P in matrix form, and we know that the K matrix is a singular Toeplitz type of matrix, and it can be easily constructed in MATLAB as long as we know the elements of the first row, because that's all we need. The elements of the first row defines, or first column I should say, defines the whole matrix. Therefore it's a singular circular Toeplitz matrix. It is time for you to test how close you can get on your system in the Hertzian case. And what I mean by this is, first, how close to a plane can you get the contact nodes to be? So you know exactly the conditions when we have contact, pressure is greater than 0, and then the deformed gap must be 0, but of course numerically we will have it to be close to 0 but not identical to 0. How close can you get? How close can you get to the dimensionless load of pi over 2 in your case? What are the restrictions here? And what about higher order discretization? So if you have a second order polynomial to discretize your pressure distribution, what would the accuracy be then? So we have seen the discretization in 1D, and it's not much different in 2D really. Well, not at least after you have defined the way you will actually enumerate your grid nodes, because this will be very important. And in this case you can see that now I have two indices I and j, and the j index is the y-axis index and the I index is the x-axis index, or x1 and x2 axes as we have here. And you can see we start with the first index is 2, 2. Well, this is MATLAB indexing. So on the origin we have then we have 1, 1. And then the first interior index would be 2, 2. If we move in the x1 direction or x direction, then we have 3, 2, 4, 2, 5, 2, up to n1 minus 1, and n1 actually not n1 minus 1 but n1 comma 2 on that row, or on that row. And then if we move up, so we increase the J index, then we are in the point x1, 2 and x2, 3, which is discretely represented by 2, 3. And now we move in the x1 direction. We have 3, 3, 4, 3, 5, 3, and so on up to n1, 3. Then moving up one more, and so on. And then we can cover the whole discrete domain that we have, that we are considering. And then you see here how we can define a centered element pressure discretization in the same way as we did in one dimension, but now we also do this centering in the y direction or x2 direction.